So I'll tell you about the progress with True North chip and the software ecosystem, which started from the DARPA Synapse project and where we are today. So we started by understanding neuroscience, and what you see here is some of the work that we did very early part of the project in terms of understanding the neuroanatomical structure. How, Karl-Heinz?
My computer.
It's right here, very safe.
I see, great. Thank you. Keep going.
This is Karl-Heinz
Yeah,
Meyer,
yeah.
co-director of the Human Brain
No.
Project, who's going to join me in the True North project now.
Yeah. I just charged my computer, that's why.
So Karl-Heinz is a good friend. So we started with understanding the neuroanatomical structure of the brain, especially the large-scale connectivity, which has guided how we have designed the communication infrastructure underlying our chips. And then, having understood the available data on the micro and macro cortical connectivity, we created some of the largest simulations. We created simulations at the scale of 100 trillion synapses using 96 racks of Blue Gene Q Sequoia, 1.5 million processors, 1.5 petabytes of main memory, 6.3 million threads. And yet, the simulation ran 1,500 times slower than real time. Meaning that a hypothetical computer to simulate 100 trillion synapses in the human brain would consume about 12 gigawatts of power. That's the entire power generation capacity of the small island nation of Singapore, just for one simple human scale simulation. So clearly, current computing isn't suited for energy efficiency and throughput of brain-inspired computing. And why is that? This curve provides the answer. On the x-axis, log scale is the clock frequency. On the y-axis, log scale is the power density. And starting from the very first microprocessor, over 3 decades, we have increased both the clock frequency and power density. But the brain sits alone in a totally different part of this curve, orders and orders of magnitude away in terms of power density and clock speed. So this is the mystery that we're trying to unravel and deliver in terms of a computational substrate. So what's the idea? The idea is, you heard about neocortex today morning, and the ability that it sort of looks more or less translation invariant through the surface of the cortex. And so this is an idealization of the hypothesized canonical cortical microcircuits that tile the surface of the cortex. Each of this essentially consists of a small module of neurons, let's say roughly about 250, 100 or so, that are tiled through the fabric of the brain. So we took this as an inspiration, and imagine a very small neural network, essentially a bipartite graph with 256 neurons, 256 axons, and 256 square synapses. And that's what we called a neurosynaptic core. A neurosynaptic core fundamentally brings together computation, neurons, memory, synapses, and communication. And therefore, already begins to bypass the limitations of the von Neumann architecture. And then what we did is we went back and we looked at the white matter, the long-distance macro connectivity in the primate brain. And by marrying the neurosynaptic core concept with the macro connectivity, we imagine an architecture which is essentially a network of neurosynaptic cores. Each core is a small neural network, a bipartite graph. They're interconnected on a chip via a network on chip, and the chips themselves can be interconnected in an endless sea of neurosynaptic cores, either in 2 dimensions, 3 dimensions, in a wafer scale, or individual chips. Same idea, fundamentally, natively, homogeneously scalable on one end, and extremely power efficient and high speed on the other hand. a paradox that one cannot achieve with von Neumann architecture. And to demonstrate the concept, in 2011, we demonstrated the first neurosynaptic core. The core could already do pretty nice tasks. For example, it could play Pong, and Todd Hilton, who was our DARPA Synapse program manager, it played with him. At the end of our phase 2, he lost. We got our phase 3 funding. Thank you, Todd. The chip, of course, was heavily featured. But then going forward, we took a core with 256 neurons. We scaled it in power by 2 orders of magnitude, 100x. We scaled it in area by over a magnitude, 15x. And we tiled not just 1, 2, 4, 8, but 4,096 of them into the TrueNorth chip. The chip has 4,096 cores in a 64 by 64 array with a network on chip, 1 million neurons, 256 million synapses, 5.4 billion transistors. So it was, at that time, the largest IBM chip and one of the largest chips made, 4 square centimeters area. It was made in Samsung 28 nanometer low power process. In spite of its computational capability, the real secret is in this chart, which shows the thermal consumption, the power density of the chip versus an FPGA on the same board, which is just passing spikes to the chip. The chip consumes just 70 milliwatts. The power density is 20 milliwatts per square centimeter. The power density of a high-end server is over 100 watts per square centimeter. So we're talking about 5,000x reduction in power. You can tile this in 3D, you can do wafer scale, you can actually or you can make it ultra small. That's the idea. And going forward, what we have been doing, so this is to catch up, and I'll tell you the new information, is we created a tiny little single chip board, size of my palm, size of an index card, with one TrueNorth Synapse chip. And now we have been giving this out to universities. And also, we have been shipping many of the boards and systems to government customers as well as commercials. And once we built the single chip board, there was a desire on part of Air Force Research Lab to build a scale-out supercomputer. So here's a design of a computer with 16 single chip boards into a chassis, 16 million neurons, 4 billion synapses. So since we built one, now we have ordered to build 2 more, and we'll be building one for Army, and we are planning to build one for Navy as well. And so that's about a single chip board and a scale-out supercomputer. But the chip has incredible capability in terms of tiling. This is the TrueNorth chip. You can just tile them seamlessly and have them connect and behave like the complex is a larger chip. So there are ports, 8 ports on each side, which allow the spikes to go between chips as if they're transparent, without need for any additional communication circuitry. And so as a result, we are building now a scale-up supercomputer with 16 chips, 16 million neurons, 4 billion synapses, that actually will be shipped to Lawrence Livermore National Lab, Department of Energy, God willing, March 31st of this year. So, it's always slip up, right? What's a week or so in research? So now this is about the hardware. So how about programming it? So currently, the dominant paradigm in programming and showing applications is deep computing, deep convolution neural networks. Now, what is the difference between these neuromorphic computing and deep learning? Well, deep learning is about capability. It's about accuracy in terms of application performance. It's used to program in an offline fashion neuromorphic computing. And neuromorphic computing is about unprecedented energy efficiency, volume efficiency, speed, and scalability. And it's used to deliver. So think about offline learning versus online delivery, inference, recognition. So the idea is, wouldn't it be nice if one could leverage deep learning to actually program TrueNorth? Now, this is a difficult problem. Why is it a difficult problem? Because to attain the unprecedented energy efficiency and the speed, we had to look at spiking neurons. Nobody knows how to do learning with spiking neurons and backpropagation. We had to use limited precision synapses, widely held belief that you need high precision. And we use canonical core-wise connectivity, whereas a lot of the networks have full connectivity or very large fan-out. So the key insight that we will publish shortly is that it is possible, even with these three constraints, which seem negative, to map both backpropagation and convolution neural networks to true north and achieve state-of-the-art accuracy, energy efficiency, and unprecedented throughput. And not only did we do this, we actually built an end-to-end workflow, a workflow that now can be taught to a programmer in about a half a day. This is a far cry. When we first started programming True North about 2.5 years ago, it used to require 6 months of residential training at Almaden. Came down to 3 months. Last August, we held a 3-week boot camp, which 30 universities and government agencies attended, and now we are down to a matter of days. So remarkable progress in ease of use. And now let me show you some of the demos. A couple of the demos I'll show you were before the deep learning work. So here, this is actually a video from DARPA NeoVision heli datasets, a helicopter flying over Los Angeles Municipal Airport, and a multi-scale pyramid of edges being extracted with milliwatts of power at 30 frames per second. Another demonstration, same sort of a data set, being able to extract luminance, color contrast, again 30 frames per second, real time. And now taking all these features, and now here's where we use deep learning, and apply them to 2 data sets. One is NeoVision Stanford data set, stationary camera. One is moving camera, moving targets. Again, 30 frames per second. State-of-the-art accuracy, much lower power than any of the existing platforms. Going forward, Street View house number data set. Again, state-of-the-art accuracy, 1,000 frames per second. And you can see this live today with my distinguished colleague, Dr. Paul Merola. Classic data set that's often used is CFAR 10 class thumbnail images. Again, a deep convolution network achieving state-of-the-art accuracy. Here we are showing a single chip version, 1,000 frames per second. So frames per second for what is out of the ballpark here. Now, why is this working? To give you an insight, here's a visualization. So this is CFAR 10 at layer 0, the data that comes in. You're seeing a very high dimensional space being visualized. And you can see all the data is bunched up. Layer 13, you can see the data begins to disperse itself in space. I won't run the videos for long. We're getting out of time here. And here's layer 25, and you can begin to see tremendous discrimination. So neural networks are fundamentally rich structures that, in spite of the surgery that we had to do for the energy efficiency, are able to deliver the fundamental accuracy and discrimination. Moving forward, this is another data set, Flickr Logo 32. It's 32 brand images collected by European graduate students, mostly beer. Karl-Heinz, what do you do out there? So another one, German traffic sign, 43 traffic signs, again, state-of-the-art accuracy. One more data set, CFAR 100. Again, this is on a single chip. Now give you another modality, voice. So this is going to be a voice activity detection.
In wage negotiations, the industry bargains as a unit with a single union.
Very simple, voice background clean.
In wage negotiations, the industry bargains as a unit with a single union.
Background.
Heave on those ropes, the boats come unstuck.
Moving forward. So now one more example where we're actually going to train the network on the phonemes.
In wage negotiations, the industry bargains as a unit with a single union.
One more
Heave
example.
on those ropes. The boats come unstuck.
The bungalow was pleasantly situated near the shore.
Okay. So, what is the surprise here? In my mind, this is an amazing result for a totally different reason. The surprise is that specification for True North was frozen in 2011, 1 year before the current deep convolution network revolution. So it really speaks to the versatility, the universality, and the power of the neuromorphic substrate. And not only are we going to be able to do this, but we'll be able to extend it into many applications because True North supports feed-forward, feedback, lateral, recurrent connectivity, as well as many kinds of neuron modes. And to teach that, we have actually been running a program called the Synapse University. Now we have 100 developers at 30+ universities and government agencies. Now, in spite of my best efforts, one university, and I'm going to single this university out, is not signing an agreement with us. So, but let that not be an excuse for you. So if you're in university and if you'd like access to True North board and ecosystem, then please send me an email and we'll do our best to make this available to you. And to make it easy for you to learn, we have a bootcamp reunion coming up in May, and I will be happy to invite you to it. Now again, neuromorphic computing is not meant to replace von Neumann computing. It's supposed to be a counterpart. So if you think of von Neumann computing as a left brain, symbolic, structured, if-then-else, binary sort of a computing, then Synapse or neuromorphic computing, brain-inspired computing, is about pattern recognition, slow, synthetic, parallel. On one hand, you have FLOPs, floating point operations per second. On our side, we have SOPs, synaptic operations per second. To give you a perspective of, since the project started where we are, project actually started in 2004 with a single person, leading from then on to an Almaden Institute on Cognitive Computing, which actually, Christoph, you were present at. And so it's really great to have you. And then from then on, we worked on the largest blue gene L, the largest blue gene P, and largest blue gene Q to carry out increasingly larger simulations. This is, of course, Henry Markham's favorite one. And then we won the DARPA Synapse project grant and worked very closely with Todd Hilton, Gil Pratt, and Dan Hammerstorm. We mapped out the wiring diagram by collecting the largest data set. We created the worm-scale chips with 256 neurons. I mentioned the simulation at the scale of human brain with 100 trillion synapses to development of the True North ecosystem. So not only do we have a chip, but we have an end-to-end programming paradigm from user interface, deep learning, down to a programming language, firmware, as well as the whole user flow and debugging tools, right? And on top of that, we have created various boards, and we are making plans by December of next year to create a 128 chip system that should happen. So we are now just at the beginning of the next generation. In the next generation, we already can imagine new chips, new software, ecosystem, new training, new systems, and even new sensors and new algorithms and applications, which will fundamentally allow us to create completely new neural networks. And we have a roadmap for building systems by using example of the scalability of True North. And the whole idea is a sort of a spiral. We went from architecture to simulation to chips to applications. And now that we have the benefit of insights, not just from our work, from work of colleagues as well, that we can actually, again, do another turn on the spiral. And the ultimate vision, which I believe will be possible before 2020 ends, is that we will be able to produce a brain in a box, which was the original vision of Synapse project, 10 billion neurons in 2 liter, 1 kilowatt. This is no longer science fiction. It is happening. So the project has received a lot of adulation. I just want to flash it in front of you real quick. But this is very important. Last fall, we had a chance to present the tiled board to President Obama, and we received a real signed letter congratulating the team, which has become a prized possession for our team. And it was presented to the House panel on science, as well as Senate panel on science. And with that, I would like to thank the DARPA program managers for their vision, their partnership. I'd like to thank our current customers, Air Force Research Lab, DARPA, Lawrence Livermore National Lab, Army, and hopefully Navy coming soon. This is a collaborative work. I saw Professor Philip Wong, who has been part of the project since very early on, Department of Energy, 8 IBM labs and fabs, and just the Synapse project itself at 6 universities, but of course now we have expanded. I would like to thank Livermore and NNSA for all the supercomputers that they gave us, and all my wonderful colleagues. It's really a joint work, and some of them at Almaden today. With that, thank you very much for your attention, and thank you for inviting me, Murad. And please remember to see my colleague, Dr. Paul Marola, today evening for the demos. John, so is the question we agreed upon, right?
Pardon?
The question we agreed upon, right?
Exactly. No. So some of us do backpropagation and spiking neural networks and some other things. But the question that I have is, right now your training is done offline.
Yes.
And I think it would be fantastic to implement all that on a 28-board chip. Do you have any plans to put that learning algorithm into the chip and accelerate that portion of it?
We certainly do.
Yeah.
And it's again, the accelerating learning has to be done with far more care than accelerating inference, as you can understand, because you don't want to tie yourself down so that you cannot explore the full space of learning algorithms. But I'm certainly happy to talk to you about this.
So
Karl-Heinz.
for your brain in the box, 1 liter, you would definitely
Two.
need 2 liters. Sorry, you would.
Karl-Heinz, this is not fair.
You would. I give you 10 liters.
Okay.
Okay, but you would still need a different solid-state circuit technology. So what will be your choice?
7 nanometers
That would be sufficient to put a brain in a box
will
of
be
10
sufficient.
liters. I see.
But just to be very fair, IBM has a huge investment in advanced process technology, right? And we're continuing to do that. And as such technology becomes available that can be integrated with the existing process, we stand ready to take advantage of it. So I'm an engineer. I'm not a scientist, and I want to make things work. So I'll accept anything that works. Thanks, Karl-Heinz.